I have some principles that could help guide us when making all these kinds of decisions of which statistical methods should we use and how should we be planning our tests. So this is kind of what I think are very important considerations that sometimes get missed in these kinds of decisions.
Looking like a baddie, I show up and make them stop. Wanna know my name so badly, cause I run this whole block. Flip my hair, move my head, show the world I'm royalty. When I walk by, they be taking bows, cause they know I'm the queen, yeah.
I was arguing on LinkedIn with a data scientist, which happens from time to time, but in this case, it boiled down to this question of whether we as practitioners in CRO should have and express an opinion on things like statistical methods or testing procedures, rather than just presenting everything kind of academically and objectively in a balanced way and always showing both sides of the argument. And the person I was arguing with thought that there's too many influencers out there who are just posting one side of the argument and not giving a fair enough unbiased treatment to all the different considerations and angles. I can definitely see his point, and I think there's a place for that. And the conversation got me thinking about, why do I have such strong opinions about something as seemingly boring as statistics? And you can see a couple of examples here. This isn't an isolated thing for me. I post about these things pretty often. So here we have, me kind of making fun of Bayesian statistics with the meme there, and a couple other posts about one versus two-tailed tests. And in most cases, I am stating a strong position about it. I'm not saying, oh, anything is fine, it all depends, and whatever you want is right for you. And I think I can answer why that is with a pretty concrete example. So I'll show you what I mean here. So here's an example of like a testing bandwidth calculation or a test planning sheet that has very strict statistics. So if you took the advice of someone like, Ronnie Kohavi, for example, or there's other people in the field that have pretty their own firm opinions of what the defaults should be. This one's maybe a little bit more extreme. So in this case, we're going with 99% significance and 90% power. So it's, on one end of the spectrum as far as how strict you would be with the stats. And then we're also targeting a pretty low MDE across the board here of 3%, which I have seen various people express that basically all your tests should have a 3% MDE. And if you go any higher, you're going to be underpowered and stuff like that. So this is just, made up numbers. They actually are sort of rounded off ones from a real site, though. And it's a pretty high volume site, like 20,000 users per week hitting desktop and 60,000 per week on mobile. And, fairly decent conversion volume in some cases, 1,600 per week desktop, 2,500 per week mobiles. And what this ends up in terms of the sample size and runtime requirements is, some of these tests are going to take more than a year. If you wanted to test homepage desktop, you're at 59 weeks here. And even sort of the more reasonable ones, if you can do a site-wide test on mobile, then you're almost at 6 months. So it's just, you might come to the conclusion it's just not viable to test on this site, even though it's pretty decent volume, really. So if we kind of look at maybe not the opposite end of the spectrum, but a much less strict approach, here's the same numbers as far as weekly users, weekly conversions, and baseline conversion rate is the same, the number of variants is the same, but we've gone with 90% significance and 80% power, and we've bumped the MDE, the minimum detectable effect, up from 3% to 10%, which I would argue is actually appropriate in some cases. So I'll dig into this a little bit more later. But you can see the effect that has on the runtime. Basically, every location on the site where you might want to test only needs 1 or 2 weeks now. So this has a huge impact on how you're going to go about your testing program and your testing strategy. If you can run tests in 2 weeks and get the insights that much quicker versus waiting for 6 months just to make sure that you're satisfying this PhD in statistics and you're being super strict with your stats as if you were making pharmaceuticals and it's a life or death kind of situation, then, you know, this is going to be a very different program. And that kind of brings me to another point, which is that we're just testing websites. We're trying to make more money for our clients or for the businesses we work in. This isn't a life or death kind of situation. We're not testing some brand new drug that might kill people or it might save people and the stakes that are involved in that. So I think we can afford to take a more balanced approach with it. And in that light, I have some principles that could help guide us when making all these kinds of decisions of which statistical methods should we use and how should we be planning our tests. So this is kind of what I think are very important considerations that sometimes get missed in these kinds of decisions. One, I think that risk and error should be transparent and out in the open. So I think there's a big difference between taking a risk that you know about and you are aware of the potential consequences versus an unknown risk that's just happening behind the scenes and you don't even have any way of measuring it or knowing about it. And I think most people would agree that this is pretty important, even if it requires a little bit of education of the stakeholders that you're involved with, just to let them know there's this percent chance of false positive and this percent chance of false negative. And by the way, I would even get in trouble with the data scientists by saying chance rather than probability, because apparently those have very different definitions. But I'm not super strict about terminology. I think as long as you have roughly the right idea about what those things mean, we don't have to write an academic paper here. We're not giving a lecture at a university. So use the words that make sense, and maybe somebody's going to correct you from time to time. So the second principle is answering the right questions. And what I mean by that is different types of statistical tests are answers to questions. And sometimes people just kind of jump into it without really thinking about what question is this particular statistical parameter trying to answer. For example, what is the p-value? That's answering the question of how often would you see a result this extreme or greater if there actually was no difference between your control and your variant, which I think is a very logical and interesting question to answer, because if you see a result, you say we have a 10% lift in the conversion rate. So then the next question is, okay, is that surprising? Or would that just happen anyway? We know conversion rates fluctuate all the time. So a 10% difference, how interesting is that really? And that's what the p-value tells you. It says the percentage of time that you would see an effect like that if there was no difference. So then if it's a low percentage, then that means, hey, this probably is a real result. That 10% lift is, as we say, significant. So that's one example where there's pretty good alignment between what you're wondering and what the parameter is actually answering. So the other important principle, which I hope everyone is doing already, but I can forgive you if you aren't because there's a lot of conflicting advice out there, is to plan your test in advance. And so that means, like on the example that I showed you, put in your weekly volume, weekly conversions into some sort of test planner, choose the effect that you're interested in being able to detect, choose your parameters of significance and power, and see what the needed sample size is and run your test until it reaches that. There's some exceptions to this. There's definitely some more advanced approaches where maybe you don't have to run it quite that long, but I'll get into that closer to the end of the talk here. And the other principle is that everything is a trade-off. This is actually true in life in general, as I'm sure you've noticed, but especially in statistics. The most common trade-off that people sort of think about is type 1 versus type 2 error, or false positive risk or rate versus false negative rate. And it's maybe a bad example because in practice, you don't really trade off between those two. If you were to keep the sample size the same, then you would. Then you're choosing how to allocate your error. Or do you want more false positive or false negative? But in reality, what people do is kind of choose their parameters, and then it's a trade-off between that and sample size. So if you want more precision, it's going to take longer to run the test. And so that's the real trade-off. I've never seen anybody say, we're going to run this test for 3 weeks, no matter what. And so let's dial in the false positive versus false negative. So like in practice, it doesn't really happen, although it is technically true that those things balance each other off. So I have a few of these different choices that you have to make, and we'll go through them one by one, and then we'll see how they align with these principles that we're talking about. So the first one that I want to talk about is Bayesian versus Frequentist. So
This is Romo Santiago from Experiment Nation. Every week we share interviews with and conference sessions by our favorite conversion rate optimizers from around the world. So if you like this video, smash that like button and consider subscribing. It helps us a bunch. Now back to the episode.
This is a debate that comes up all the time. And there's people that are very strongly on the Bayesian side and the Frequentist side. And then there's people that just think, it doesn't matter, choose whatever you want. It's all the same. And in a way, they have a point. I'll illustrate that with an example in a second. But you can probably tell from my little image here that where I'm going to come out on this Frequentist versus Bayesian debate. I don't mean to knock Bayesian in general. It's a very useful method with lots of different applications where it absolutely makes sense. And I just don't think it works very well in our context, which is website A/B tests. So all these different choices I'm going to show you, that's what I'm talking about. We're running A versus B, or maybe A versus B versus C, or more variants, but it's an A/B test on a website. In a lot of cases, this could apply to in-product or in-app testing as well, depending on the metrics and stuff. But just being within this context actually helps a lot with these decisions, because we're narrowing down the possible field of possibilities quite a bit. We're not running all sorts of different random types of statistical tests for lots of different situations. For the most part, it's a difference of means. We're looking at conversion rate of control versus conversion rate of variant. And we want to know, how significant that result is. So let's look at just a quick example of Bayesian calculators. So this is from Dynamic Yield Labs, and it's a little bit of a rarity because they have a sample size calculator that's based on Bayesian statistics. And usually even people that use Bayesian, they kind of admit that Bayesian isn't all that useful for test planning. So maybe it's useful after the fact, but the test planning doesn't really work that well with it. I'll get into that more in a second, but let's just look at a quick example. So say you have a baseline conversion rate of 5%. Your expected uplift is 10%, which is in a way similar to MDE, but not quite. You shouldn't set your MDE to be exactly at your expected uplift, because then if you're off by even a tiny little bit, then you're going to have inconclusive results. But let's just kind of skip over that for now. So 2 variations in the test, including control, and 2,000 visitors per day. So we can see what it spits out here. Calculating. Now if we scroll down, we can see what it says. So it went with a 95% confidence level, which we didn't get a chance to set that, but that's fine. It's an acceptable default. It says you'll need 30,000 visitors, which will take approximately 2 weeks. Okay, so 2 weeks to run this test. So I'll show you with just more generic statistics of what this same kind of scenario would look like. So we have 14,000 weekly users, so same as 2,000 per day, and 5% baseline conversion rate, targeting an MDE of 10% with 2 variants including control. Now, in a typical scenario, you'd be looking at 80% power, 95% significance. And so this is showing a runtime of 4 weeks, and it's closer to like 50,000 on the sample size in total, so almost 24,000 per variant. So why is there such a difference? Like, why is this Bayesian calculator saying you only need 2 weeks, but then if you run Frequentist stats, it says 4 weeks? The answer to that is that Bayesian doesn't actually have any concept of statistical power. If you remember from your stats courses, power is the probability of detecting a true effect if it exists. So you could have a real effect of, say, 8%, but it would show up as inconclusive anyway because your test didn't have enough sensitivity, shall we say, to detect that lift. So this kind of gives us a clue. So since you can't specify like 80% power for the Bayesian, what it's actually doing is it's telling you the point at which, the exact point where you would reach significance. And so in frequentist terms, that's the 50-50 point. So say the true effect is 10%, then if you get a result any higher than that, you'll have a significant effect. Any lower than that, then you will have an inconclusive effect. So we can actually get this to align with the frequentist if we just put 50-50. And I think it should be obvious that this isn't a very good way to run a test. Like, if you have a true effect, you don't want there to be a 50-50 chance of getting a significant result, right? So that's why the standard in test planning is 80% power. So then there's only a 20% chance that you'll miss it. And then if the effect is much higher than that, then that actually goes up anyway. If we drop the power down to a 50-50 chance, then the runtime comes down to 2 weeks, which is a little bit closer to the Bayesian. And the sample size is actually less than the Bayesian one said. So there's some differences in the calculations, obviously, but it gets us pretty close. So that's an example of the first issue with Bayesian here, where there's no concept of power and it doesn't really say anything about false positives versus false negatives. It gives you a percentage of what is the chance that this variant will beat the control. Another thing that's important to know about Bayesian is that it's built for situations where you have prior knowledge that you can incorporate into the stats calculations. But the vast majority of Bayesian calculators out there for CRO, they obviously don't know anything about your testing program or which tests you ran before or what you might know about the tests. And I would say that's actually kind of appropriate, because if you ran a test last week, then what does that really have to do with the test you're running this week? Maybe if you're testing the same thing and you think you're testing it on pretty much the same people, you could make an argument that information from a prior test should influence how you look at a new test. But I really don't jive with that line of thinking. Like, to me, each test needs to be evaluated based on only what happens in the test. And then if you want to make meta analysis or comparisons between different tests, you're free to do that. But at least you know that the foundation is this test is significant or not based on the details of this specific test, of the data that we have for this test. But the problem with the Bayesian way of looking at things is it ends up being kind of like a license to use bad practices. Because if you use Bayesian with no priors or non-informative priors, as they say, then it actually aligns quite well with frequentist statistics. So if you just look at the significance after calculating the p-value, it's going to be pretty much the same, if not identical, to what you get from a Bayesian calculation. Not for test planning because of the power thing that I was talking about, but if you're analyzing after the fact, it almost won't matter. And you can try this. If there's a calculator that has Bayesian mode and frequentist mode, pop in the same numbers and you're going to get pretty much the same percentage. But the problem is with Bayesian, it's kind of advertised as being easier to understand, and you don't have to care about things like p-value and what that means. You can just take the percentage, say it's 80%, and just say there's an 80% chance that this variant is better. In a business context, executives are going to hear 80% chance. Like, when do you ever in business have like an 80% chance of something being a winner? So that might sound pretty good. But if you're actually doing what I'll call proper analysis with Frequentist, it's very rare that you'd be okay with the 80% significance level, like a 20% chance that it's a false positive. So that's kind of the problem. Like, with a sort of incomplete application of Bayesian, you're not using any of this prior information, and it basically becomes the same thing effectively as Frequentist, but for some reason the interpretation is allowed to be different. There are implementations out there that do take into account prior data, and a couple of examples would be Google Optimize or Optimizely, one of the best known testing tool providers. They have their proprietary stats engine, and I've combed through the white papers on it and confirmed this. And what they do is they will use information from other tests that are run on the platform. And that's not just limited to your account. So these other companies are running tests using Optimizely, and the data goes in there. And then when Optimizely is deciding whether your single test is significant or not, it's using information from other people's tests to decide that. And you don't get to know whose test or what those tests were like. You have no idea of like what sort of approach all these other people are taking, or how applicable their tests actually are to your test, because these proprietary stats engines of these various tools are basically just a black box. Like, they're not going to give away their secret sauce and let you know exactly how these things are calculated. So you basically just have to trust them, that they're making some good decisions, and that any priors that they're taking into account for their Bayesian stats are relevant to your case somehow. To me, that's just not a very good approach. Like, I would way rather just use industry standard statistics that are easy to explain. If anybody else is coming into it, you don't have to say, oh, it's just this magic that's happening behind the scenes. You just say, yeah, we calculated the p-value, here's what it is, and there you go. There's no question about it. And that's kind of another thing that's happening that you might not really think about, is that, say you decide we're going to use Bayesian statistics to analyze our tests. That doesn't make the frequentist stats go away. You can always run the same numbers through a frequentist calculator and you will see the results. You'll get the actual p-value. Using Bayesian, because it's easier to explain and easier to interpret, allegedly, that doesn't mean that the frequentist stuff doesn't apply. It's still there. You can check. You can just always run your data and see what frequentist stats are saying. And pulling the wool over your eyes is not some sort of solution that doesn't solve the situation for you. So let's see here. How does Bayesian align with the principles that we established before? So risk and error should be transparent. It's a big red X for that one, because there's no conception of some of these errors in Bayesian. It just kind of all boils down to one percentage. You don't get to know about statistical power and false negatives, and you sort of get an idea of false positives, but you kind of have to infer that, and it's not really correct according to the definitions of what Bayesian is telling you. So yeah, it fails on that one. Answering the right questions, I was tempted to put an X there too, but you could make the case that Bayesian is answering the question you want. This is kind of a whole other area about posterior probabilities versus prior probabilities and stuff like that, and there's just not time to get into all these weeds. So I'll just leave off the X for now and say that you could make the case that Bayesian is answering at least some of the right questions if you want. Planning your test in advance, well, because it doesn't give you any control over the different types of error, I would say it's basically impossible. But you could, I guess, use that Bayesian calculator, and it will give you a very rosy picture about how long you have to run your test. And then you'll end up with a lot of inconclusive tests that you just don't understand why, and it's because of that implied 50% power kind of issue. So, I don't think it really qualifies there. I don't think there's many people out there that would try to make the case that Bayesian is good for test planning. And then everything being a trade-off. So, maybe I should have put a smaller X on this one, because if you're aware of the trade-offs of using Bayesian, then you can sort of work with it. But in my opinion, like that example that I showed you, it's a bad trade-off. You're going too far in the direction of not caring about your stats or not being strict enough about your stats in order to get a really quick runtime. And as in with the risk and error not being transparent and the lack of test planning. But to me, this sort of example is too far on the lenient end of the spectrum, and I'm in the middle. Like, I'm not super strict at all. I just want to make sure these principles are actually being applied. So the next decision that I want to look at is, one-tailed versus two-tailed tests. This is another one where a lot of my colleagues or people in the industry just don't seem to care. They don't really seem to think that it's a big deal. And then there are actually some people that are very strongly on the one-tailed or the two-tailed side of things. So first of all, what is it? As you know, like the bell curve. Oh, I'm upside down. Okay, let's try this. So you have your conversion rate. It has a point estimate, right? And then there's the bell curve on either side. And that represents the conversion rate fluctuating through time. There's always going to be variance. No one has a completely consistent conversion rate. So then when you're running a test and you have a variant, you want to figure out, which side of the bell curve are you looking at? So a one-tailed test is looking at one side at a time. You're trying to see whether or not the variant is better than control by some margin that you choose, your MDE, and decide whether it's significant or not. And so there seems to be a lot of misunderstanding about two-tailed tests. Like, people think that if you don't know what direction the effect is going to be, that you need to use two-tailed. But really what two-tailed test does is it just tells you whether it's different, right? So it's basically answering the question, is the control the same as the variant, or is the variant better or worse, without actually telling you which one it is? The example that I like for this is like a production line. Say you have this manufacturing process and you're making a part and it needs to be a certain size, and you have a certain tolerance for that. Like, it's okay if it's 10 thou over or 10 thou under. If it's more than that, then you need to stop the production line and actually figure out what's going on, because you're producing a bunch of parts that are out of spec and your customers aren't going to want them. So a two-tailed test is kind of made for that type of scenario, where it's like, is the variant different? Is it bigger or smaller than what we want? Yes or no. It doesn't actually tell you, is it bigger? Yes or no. Or is it smaller? Yes or no. It's basically just is it different? So that is one of the kind of understandings of it. There's other ones as well. Like, people say that a two-tailed test is more accurate than a one-tailed test, and that if you want to know if you have a significant drop or a significant lift, that you should be using a two-tailed test. So there's some issues. We'll cover them right here. So in reality, nobody is interested in the question that two-tailed tests answer. And, I'm painting with a pretty broad brush there. So what I should say is, in the context of website A/B tests, in CRO, we can narrow it down further and further if you want, but I think that's probably good enough. Nobody really is interested in that question of, is it different, yes or no? Because we want to know whether it's better or whether it's worse, right? We're interested in one side or the other. That kind of leads me to the next point, which is, how many actions are you actually going to take based on the test results. So in most cases, you're running either a superiority test where you want to prove that the variant is better in order to justify putting the effort into implementing it on the site, and so that that it's going to have a positive effect if you do. Or you want a non-inferiority type of case, or a do no harm test, where for some reason or another you want to make this change, but you just want to make sure that it's not going to harm performance too much. And usually it's one or the other. It should be one or the other, really. And this should be decided before the test. And when people use a two-tailed test, usually in practice that ends up being a way to avoid committing to that in advance and committing to your decision criteria. And here's kind of how it typically goes. You'll run a two-tailed test, run it for a while. Maybe you did some good planning, maybe you didn't. And there's a little bit of a lift. Maybe there's a 1 or 2% lift, and then your MDE was actually 5% or something. So usually the conversation goes like this. Okay, we saw a positive effect. It wasn't significant though, but at least we know it's not significantly worse. So we can go ahead and implement this anyway. Even though we didn't prove it's better, at least we proved that it's not worse. And I've been guilty of this myself before I knew better. And I think lots of people do this. And what's the problem with that? Well, if you have a 5% MDE on the positive side with a two-tailed test, you also have a 5% MDE on the negative side. So an inconclusive two-tailed test could have, say, like a -3 or -4% true effect that you just didn't detect with the test. So are you actually okay with rolling out something that might have a 4% drop in performance? Probably not. Maybe. I mean, if you are, then plan your test that way. I can get into this a little bit later, but there are ways to run an actual non-inferiority test where you explicitly set how much of a negative margin you'd be okay with. And there's advantages to that too. You get to run it a lot quicker. So yeah, that's it's definitely better to decide these things in advance. Like, what type of test is this? Do we want to prove it's better, or do we just want to prove that it's probably not worse, right? And a two-tailed test doesn't really do that for you, and it can be kind of dangerous if you don't realize this. You don't realize the risk of having a drop in performance that you didn't detect. Another thing that people don't really realize about two-tailed tests is that they introduce a third type of error. So this is known as type 3 error or sign error. And two-tailed test, like I said, isn't telling you whether it's better or worse. But what people usually do is, if they see that there's a positive lift, then they sort of infer, like, okay, sure, the statistical test itself isn't telling us whether it's better or worse, but there's a positive effect. So we can just kind of assume that it is actually better, and that if it says it's significant, then that means that it's in the positive direction. When you're using a two-tailed test, this sign error comes into play, and it's pretty small. Like, I'm not going to exaggerate it and say that it's a big risk, but it's there, and it's error that's not accounted for. And from my principles, that just doesn't work with me. I don't like having hidden types of error that are just going to sneak out and rear their head when you least expect it. So let's give a little bit of a score here for two-tailed tests and how they align with our principles. So risk and error should be transparent. I think it's a big no for that one. One, because of that type 3 error that I was telling you about, the sign error. And then the other thing is that, say you run a two-tailed test at 95% significance, what that actually means is that on any of the two tails, it's equivalent to 97.5% significance. Or if you're looking at, your alpha, say you set your alpha to have a 5% false positive rate, on each of the individual tails, it's actually only a 2.5 false positive rate. And the people that push for Bayesian and say that it's more accurate, that's why they do it, right? Because if you just run it for the same significance level as a one-tailed test, then on each tail you're actually sort of getting more precision. But if you want more precision, you can actually just increase your significance level to 97.5 on the one-tailed test. And if you do it that way, it's transparent. You know what your risk is. There's not this sort of weird thing where it's like, yeah, we ran 95%, but it really means 97%, right? So because of those considerations, I just think that two-tailed tests don't really jive with that principle. There's just like these couple of weird things with the error being a little bit obfuscated, and I like the error right out in the open. So I'm giving it an X on that one. Does it answer the right questions? No, it answers a completely wrong question that nobody actually cares about. And the people that use two-tailed tests actually admit this. And if you press them on it, they actually say, well, what we're really doing is two one-sided tests. And one-sided and one-tailed, two-sided, two-tailed, those are kind of equivalent terms. And there's an acronym for this, it's TOST, so two one-sided tests. Right away, they're not actually even using the two-tailed test because it just doesn't make sense. Like, no one can really make the case that it's applicable to this situation. So yeah, no, it's not answering the right questions. And even the people that use them and push for them, they know this, and they basically just use a two-tailed test as sort of a hacky way to run two one-sided tests. Okay, so what about planning your tests in advance? Well, maybe I was a little bit too strict in giving the X's here, because you can actually do pretty good test planning if you're doing it with a two-sided test or a two-tailed test. It's just that because those errors are kind of transparent, that you might run into problems. Like, you think you're setting it up for 90%, but you're actually setting it up for 95% on the positive tail. And so it's just not quite as straightforward as it would be if you were just using like one-sided. So maybe I should revise that one to be a little X, kind of like this trade-off thing here. So yeah, how does it work in terms of trade-offs? It's not as bad as some approaches, but I'm still giving it a little mini X here because I don't think it's an appropriate trade-off. You're basically running your tests longer in order to ask the wrong question, right? So, running your test between, say, 20 and 60% longer, depending on the significance level you're looking at, in order to answer the wrong question of, is it better, yes or no? Whereas, if you planned your test properly, you actually get to run it quicker and answer the question that you actually want an answer to. Okay, a lot about what I think are some things you shouldn't do, approaches you shouldn't do, and how they kind of failed to align with our principles. So let's change gears here and look at the positive side of things. So what should you actually do? How can you actually approach planning and analyzing tests in a way that aligns with those four principles? So this is what I would say. Plan your experiments in advance. So do this with Frequentist statistics and a one-tailed test. And there's two different scenarios. One is superiority, one is non-inferiority. So I can get into that a little bit in the next slide here. But the one-tailed test, it isn't actually limited to only looking at the uplift. You can look at both sides. You just run two one-tailed tests. You run one in the positive direction, one in the negative direction. So if you see a lift, you want to see if the lift is significant, do a one-tailed test on the positive tail. You see a drop, you want to know if the drop is significant, do a one-tailed test on the negative tail, right? So that's post-analysis, obviously, but in the planning stage, that means you just do a one-tailed sample size calculation. And it's straightforward, it's easy, there's lots of different calculators that you can use for this. And then so it just becomes a question of which parameters should you use. So power level, pretty much everyone is using 80% power. It's kind of the default. Very few people are actually deviating from this. If you agree with me that false negatives are to be avoided, that they're costly, then And if you have the volume for it, then maybe you want to up your statistical power to 90%, or you could go higher if you want. But even just going to 90%, you're doing more to control false negatives than 90% of people in the industry. And then significance level. So what significance level should you go with? I don't think there is one straight answer for this. The default of 95% is fine. So a p-value of up to 5%. But this should depend on how much risk you and the stakeholders that you're working with are comfortable with. And this is also going to be a trade-off between runtime. So if you're in a situation where you don't have much traffic, then accepting lower significance, accepting a higher risk of false positives is one of the levers that you can pull so that you don't have to wait for 6 months to get your test results done. So I wouldn't go lower than 90%, probably. I think like a 10% false positive rate is pretty good if you're in a low volume type of scenario. If you're in high volume and you can afford it and you can afford the test runtime, then you can go higher. 95% is a good starting point. You can go to 97.5 or even 99. And once you get into a really high volume website, then that doesn't actually end up costing that much. Like, you're not sacrificing a lot of runtime to go with a pretty high significance level if you want. So it all depends on context and strategy. And, if you don't want to think about this stuff too much, then just go with 95. It's a perfectly safe significance level for most cases. And then the next parameter that you have to figure out is your MDE. So some calculators frame this as your expected uplift, which is just wrong. Like, that's not how it works. You're supposed to choose the effect size, the smallest effect size that you want to be able to detect. If you go like really small, like most people say, well, I want to detect any effect. Even if there's a 1% lift, I want to detect that, or 2% or something. Well, plug that into your calculator and see how it works, because this has probably the biggest effect on how long you're going to have to run your test. Like, I've worked on very high volume websites where we tried to detect a 1% lift, and it was still resulting in like multi-month long test run times. And so, we bumped it up to 2 or 3% in some cases, and that got it into a better kind of neighborhood. But in sort of like medium to lower traffic sites, probably you're going to need to be in the 5 to 10% range on the MDE. And often at the beginning of a testing program where the site hasn't been optimized and there's a lot of low-hanging fruit, then you can get away with 10%. Like, it's not uncommon to see lifts bigger than that in a completely new optimization program. But once you've kind of dealt with the obvious stuff and you're having to do like deeper and deeper research to get insights and turn into test ideas, and you're optimizing things that have already been optimized and you're trying to level up even more above that, then you're going to have smaller effects. And so if you don't lower your MDE, you're going to be missing a lot of true effects. You end up with a lot of inconclusive tests, and that's pretty depressing for everybody. You wouldn't want to go much higher though. Like, if you set your MDE at like 20%, then you pretty much really need to knock it out of the park. Like, every test is going to need to be in the 25-30% range in order to even detect it. So if that's what you have to work with, then it's possible that doing A/B testing is just not feasible for this context. Like, you need to wait a year or two until you get more traffic, or you need to increase your ad spend or something. You need to get a lot more volume to work with so you can get that MDE down to a reasonable level. And then, analyze your tests with the same parameters that you chose in the beginning. So I'll show you how this works in practice. So here's the same example we started with of a website where we've kind of already mapped out the weekly users and weekly conversions for all these different possible testing locations. So site-wide, homepage, product list pages, product detail pages, cart checkout, and then maybe you have some random blog page or landing page that you want to calculate as well. And so you can just plug in the conversions there. So, let's get this to kind of more reasonable starting point, 95%, 80% power. And let's say like bump this MDE up to 5%. And this gives us a fairly reasonable landscape for testing. So, if we want to run site-wide tests on mobile, it'll take 4 weeks. Homepage on desktop is kind of lower traffic, so that's going to take like 3 months almost. And that's, maybe pushing it. Maybe we don't really want to wait that long. So you can just kind of play with these parameters and see how that pans out in terms of how long you need to run these tests. Maybe you want to bump everything up to 8%. You're okay with missing a few effects, and you think that you're going to have big lifts. So, that brings the runtime down to 3 weeks, 2 weeks, 4 weeks, So yeah, using a tool like this is one we developed at Qualitative, but there's other similar things where you can kind of plug in your numbers and do some test planning. Sometimes they're called testing bandwidth calculations, or sometimes it's just pre-test planning or that sort of thing. And play with these different parameters and see how they look, and then you can get an idea of, like, if we're going to run a test on desktop cart, we're going to need 3 weeks with these parameters. And, there we go. In advance how long it's going to take. And then let's say, that's the actual case that, let's pick a bigger number. Let's say you ran a site-wide test on mobile, something in the header, something obvious, everyone's going to see it. And you wanted an 8% MDE, and these are the conversion numbers. And then after you run that test, right? So let's say you ran it and you got to your required sample size, and then you can pop this into an A/B testing calculator, or this is our other template at Qualitative, which is for specifically test analysis. And the way that this works, we plug in the variant number, so 0 for control, 1 for the variant. And let's say we got 46,000 users in both control and variant. And then we had 2,300 conversions in control. And then let's say we got 10% lift on that one. So that would be 2530 conversions. And the rest of these numbers just populate for you. So you see a conversion rate of control, 5%. Conversion rate of the variant is 5.5. The effect size was 10%. Your p-value is quite small, 0.0003. You're over 99% significance with, your significance threshold was 95. Your power is 80%. And then it also tells you what was the actual MDE. And, this is a little bit lower than what we did in the test planning because our traffic was a little bit higher. So this is just kind of a useful data point to see how your actual test compared to what you had planned. So if you ran a test and then MDE was a lot higher than you expected or than what you planned for, then it probably means that you didn't hit your sample size. Or it could mean that the conversion rate was lower than you expected in the test. So if your baseline was 5%, but the real conversion rate in the test was only 3 or something like that, then that's going to affect the MDE too. So yeah, there you go. It's pretty easy. Like, once you've gone through the process of planning the test, then the analysis side of things, it's really just pop in the actual numbers, do some quick checks, make sure you hit your sample size, and there you go. You have some numbers you can report. So there's kind of next level stuff with this good enough approach to test statistics. Superiority versus non-inferiority is one that I mentioned a couple times. So it's a little bit more challenging to calculate, but not too bad. Basically, the way it works is you decide what your non-inferiority margin is going to be. So you can say, we're okay if there's an undetected 1% drop or a 2% drop, or you probably aren't going to be comfortable with 10%, but it's up to your context and your appetite for risk. So you set that margin, and then it calculates the lift from there. So instead of having to have a 10% lift from 0, it has to have a 10% lift from -2. So it's basically just, it only needs an 8% lift. And so this can actually really drastically reduce the amount of time that you have to run your tests compared to a superiority test. And that can be beneficial. It's actually enough savings that you could run a few non-inferiority tests and then later group all those together and run one superiority test. So that can be an option in your tool belt that will definitely increase your test velocity. The other one is sequential testing. So this is kind of a cool approach where, say you plan to run your test for 4 weeks total, you can actually check in on it every week. And if it's either doing really well, better than you expected, you can stop the test early and call it a winner. Or if it's just doing really badly, then you can stop it early and call it a loser. And the approaches you take to this actually adjust the statistics, because if you were to do that normally, you'd be inflating your error rates. It's a thing called peaking. It's been written about this already. So it's not like looking at tests just magically makes the error rates change. It's just looking at it with the intent to make a decision about it. It ends up being like you're doing several tests actually and just cherry picking the one that shows you that there's a winner. So there are approaches that actually control for this error. So you can do this the proper way. The good practice, it's totally legit. And I'll share a couple of resources to that. And then the other kind of more advanced thing is, if you're testing more than one variant against control, you are also potentially introducing more error. And there's a very efficient way to correct for this, which is called Dunnett's test. There are other correction methods like Bonferroni, and these ones are too conservative, so they don't really fit the trade-off very well. You end up having too long of a run time than what you really need. And Dunnett's test is actually the one that's the most applicable to the scenario of comparing multiple variants against a common control. It's not easy to calculate though, so you need to use a tool that can do that for you. And one that I'd recommend is Analytics Toolkit. That brings me to some resources for you. Analytics Toolkit is actually a really good resource for lots of this stuff when it comes to learning about A/B test statistics, and their actual paid tool, which is kind of like a test planning, calculating, everything with A/B test statistics. Pretty good. It's pretty reasonably priced. I use it myself when I'm not using my own templates, so highly recommend it. Specifically, there's a couple of articles here. So one about Frequentist versus Bayesian. There's actually a few articles in this series that all kind of touch on different aspects of this debate. I recommend at least checking out the one here, and if you're interested, keep looking at the other ones. There's also one for one-tailed tests versus two-tailed tests, and actually the author, Georgi Georgiev, has dedicated an entire website to this whole question. It's called onesided.org, and so that's another pretty good collection of articles on that topic. And a couple of more goodies for you here. The templates that I was using in this talk, those are ones that we developed and we offer for a very reasonable price, and the link is right there. As I mentioned, Analytics Toolkit itself, the SaaS product, is very good for test planning and analysis, especially for the more complex cases where you have sequential testing or you want to correct properly for multiple comparisons. Let's kind of take care of for you there. And specifically on sequential testing, there's a blog article about it that talks about, how much faster you can run your tests on average. That it's a whole bunch of different simulations. 80% faster claim actually does hold up, as you'll see. There's also a more simple, kind of lightweight approach to sequential testing that's on the CSL blog. It's called Peak. Sequential testing can help with peaking. And it's basically you just kind of do an adjustment to your significance level based on a few things. So there's just a table there, and you just adjust it based on what the table says. It's a pretty simple way of doing a sequential testing approach. Like if you want to check on it every week instead of just at the end of the test and adjust your stats properly, this is a pretty good way to get started with that. Also, I have a couple of bonuses for you here. So one of them is the same formula that's in our template for test planning, single cell portable formula in Google Sheets. So it just kind of depends on putting the right info in the cells next to it. And then it'll tell you what sample size you need per variant, or the volume that you specify and stuff. So you can build your own template around it if you want. Yeah, just get in touch with me on LinkedIn. If we're not connected already, connect, send me a message, and I will give you this formula and give you some pointers on how to use it and how to work it into a template if you want to build your own. And another thing is for Analytics Canvas, I actually have a little link here that you can use to sign up. And then instead of I think it's normally a 2-week trial, you can actually get 2 months for free. And you have a higher quota of tests you can put in there in order to kind of tires and get familiar with the platform and stuff. So there you go. There's a link for you. Go ahead and grab that. Okay, well, if you made it this far, thanks for watching. I hope this was kind of helpful to provide some sanity to all the statistical madness that's out there and all these different questions that you have to answer and different methods that you can use, and hope that the principles that I outlined kind of provide a guide for you in answering all this stuff. And thanks for watching. Here's how to connect with me.
This is Romo Santiago from Experiment Nation. Every week we share interviews with and conference sessions by our favorite conversion rate optimizers from around the world. So if you like this video, smash that like button and consider subscribing.